said we use the law of conservation of momentum when there's an explosion or a collision when there's a jeune. So we looked at a few examples. Here we had a collision, so our first approach was to write down the sum of all the momentum before equals the sum of all the momentum afterwards. And we asked before the collision what was moving, mass 1, mass 2, or both, stuck together or separate. Same thing after. And it looks like I think we left off right here. Example 7. Example 7. A 1.2 times 10 to the third kilogram car traveling 33 meters per second collides head-on with a 1.8 times 10 to the 3 kilogram car traveling 22 meters per second in the opposite direction. You know what? Because I've gone on my vector rant, I would recommend underlining in the opposite direction. I think that's probably going to be important. If the cars stick together, what's the velocity of the wreckage immediately after the impact? Am I going to use impulse F delta T equals delta P? No, there's a collision. You know what this is a job for? Conservation of momentum. So how did we write that? We said this. The sum of all the momentum before the collision equals the sum of all the momentum after the collision. Jeff, you were away. We said that symbol there is an abbreviation for the total or the sum of. It's a summation symbol. Really handy shorthand. Before the collision, what's moving? Car 1, car 2, or both? Both. Stuck together or separate? So let's write down as a vector equation the momentum of mass 1 initial plus the momentum of mass 2 initial. Does that make sense, Anthony? Wham! They collide. He doesn't even twitch anymore. It took 3 years, but he doesn't even twitch anymore. After the collision, what's moving? Mass 1, mass 2, or both? Stuck together or separate? Okay, so I'm going to go like this. Momentum and here, I've broken each momentum side up into its momentum constituents. I always pause. Because starting next lesson, Kylie, it's going to get all different. Because next lesson, we are going to have angles and directions. So I want to build in the habit right now, Sarah, of saying, stop. Does this question mention any angles or norths of souths or easts of wests or thetas? No. If it did, the rest of our approach will be very different. That's Tuesday. For now, does this question mention any angles? Any north of south, east of wests? Any thetas? Nope. Then I can do this still with vectors, but because they're in a nice straight line, the math is going to be limited to, I'll let one way be positive and one way be negative. Momentum is what times what? Momentum is what times what? Oh, pen stopped working for a second there. Let's do my traditional. So, momentum is mass. Oh, no, I already did that, Mr. Dueck. I want to write M1 V1 initial plus M2 V2 initial. How would I write the momentum of both? Well, I'll treat them like one big uber mass. I'll go mass 1 plus mass 2 V final. And again, I mentioned the other day, but it's worth repeating, I'm being much more careful with my vector notation. What am I trying to find here? V. Which one? What am I trying to find here? V final. How would I get the V final by itself? So it's going to be M1 V1 initial, and that's the vector, plus M2 V2 initial, and that's the vector, divided by, okay. Well, we've reached the plug and chug stage. Looks like V final is going to be mass 1. Kai, what is mass 1? Sure thing. What's V1? Plus mass 2, V2, 22 is wrong. Why? Okay, we have to, and I said V on purpose. What I didn't say was speed or velocity. I didn't want to give you the hint. It's velocity 2. As soon as you let the first one be positive, I have to make that one negative, which is going to totally change my answer. Divided by. Now, when you crunch the numbers, you're going to see I cooked these numbers on purpose to make a very specific type of head-on collision. What do you get? You get 0. Try it. By the way, on the test that you guys just wrote, I saw a lot of kids with an equation like that, all the right numbers, wrong answer. My rant last unit about it's important for you to try these on your calculator fell on some deaf ears. Should work out to 0, I think. Which is okay. Here's what we're saying, Anthony. You had one smaller car coming in faster, one bigger car coming in slower. They hit head on, bang, and they didn't move after they came to a dead stop. Now, if the smaller car had been going faster, which is I'm going to represent with my right hand on your left, would have done that. If the bigger car had been going a little faster or had been a bit bigger, it would have done this. But here I cooked the numbers, head-on collision. Okay? By the way, we're going to give this notion of the wreckage sticking together a special name. We're going to give the notion of the wreckage bouncing off each other a special name as well. They're two different types of collisions. You'll learn that name next lesson. Example 8. Example 8. What impulse must be imparted to a 145-gram baseball to change its velocity from 40 meters per second south to 40 meters per second north? Now, it is true that hitting a baseball is a collision, but Carl, what's the second word this thing is asking me to find? Impulse. I'm going to start out then with, by the way, when you see impulse, what's that another word for? So I'm going to start out thinking to myself, okay, I can either go this and go final minus initial, or, don't write this next bit down, I can go force times change in time. Either of those is an option. Look at what they gave me and ask, okay, which approach am I going to use? Am I going to use the one that goes final minus initial, or am I going to use the one that goes force times time? And really what you're saying is it's all about the velocities. Did they give me a final and initial velocity, or did they give me a force and a time? I hope you'll agree they gave me a mv final minus mv initial. Is that okay, Noah? Mass 1, 145 grams. What's that, Noah, in kilos? 0.145. What's the final velocity, sir? Which one, 40 or 50? 50? Okay. Minus. You said mass 1 was 145 grams, or 0.145. What's the initial velocity, sir? Ah, wait a minute. I don't see it. Where'd that negative come from? Ah, south. And you can see it actually kind of, sort of makes sense. See, here's what we're really saying, Noah, look up. When the baseball is coming in, now north and south is awkward, but I'll just pretend it's coming in this way. The bat, first of all, has to stop it. Then it has to give it momentum going in that direction. It's a big change in momentum. Jordan, do you notice I have a minus minus? What's a minus minus really the same as? I'm going to get a bigger answer with this, which I should actually now that I think about it. What is the impulse? $13.1? 13.1 what units? Yep. I would also take Newton seconds, but again, since I used mass and velocity, that's the unit that's in my brain, but Newton seconds also works. Hey, Alex, what does B want me to find? What did I find in part A? I'm thinking maybe there's an equation that has impulse and force. This one. Another way that impulse is defined is force times time. What did you say this is asking me to find, Alex? Is this question mentioning any weird angles or anything like that? Then you know what? Get the F by itself. How, kiddo? By? Thank you. It's going to be the impulse divided by the time. In fact, I think I told you guys last lesson that was actually Newton's second law. That was his force equation. He was much more interested in impulse. I already found the impulse. It was 13.05 over. The time is 1. Does anybody have their formula sheet? Millie is on your formula sheet. It's 10 to the what? I think -3, is it? Yep. Now, I tried to make these numbers up reasonably. 50 meters per second, the final velocity. Well, first of all, the incoming velocity, 40 meters per second. That's about an 88-mile-an-hour fastball. So I tried to make this roughly major league pitcher-ish. And then I looked up about how fast a home run would leave the bat. Now, we're assuming it's a line drive. I didn't want to have the ball hit at an angle and come shooting up. That requires, okay, that's next lesson. For now, we're keeping it nice and hitting the ball squarely and all that. Anyways, what do you get? Oh, I can do this in my head. I think you'll get 13,100 newtons. Is that right? Is that big? Would you want to get hit by a baseball bat? And you know what, though? That's a fairly big... Well, you know what? Change it to kilograms. Divide that by 9.8. That's the same as having how many kilograms dropped on you. 1,300. Yeah, you know what? That would be enough to do damage, possibly kill you. And yeah, a baseball bat would do damage, possibly kill you, depending on where it hit you. So I think these numbers are about right. I was trying to make up reasonable numbers. Moral of the story is if someone's swinging a baseball bat, get out of the way. Pardon me? Yeah. Or just always hang out with people that are slower than you. Right? How do you avoid getting eaten by a bear? Always walk with someone who's slower than you. It's really that simple. You gonna make it, kiddo? You sure? Do I need to yell again? Good. Example 9. So again, momentum is great for collisions. So here we're going to rear-end somebody in traffic. A 2,000 kilogram car traveling 15 meters per second, not very fast, about 30 miles an hour, about 45, 50 kilometers, so city speed, not freeway speed. In fact, back road city speed, so subdivision speed. Rear ends another car of mass 1 times 10 to the third kilograms. The other car was initially moving 6 meters per second in the same direction. Oh, so it was traveling slower, and this person bumped into it from behind. What's their common velocity if the cars lock together during the impact? Is there a collision? This is a job for conservation of momentum. The sum of all the momentum before the collision equals the sum of all the momentum after the collision. So before the collision, what's moving? Car 1, car 2, or both? Both stuck together or separate? So I'm going to have momentum 1 initial, momentum 2 initial. Bam! They collide. After the collision, what's moving? Mass 1, mass 2, or both? Stuck together or separate? Stuck together. Now, if they were separate, I would just go momentum 1, don't write this down, final, and momentum 2, final, and then I would say, okay, are there angles or not? I would get by itself, whatever I needed to get by itself. Or if there were angles, I'd be dulping and hoping I could draw things and add them tip to tail and get some kind of a picture. But since they're stuck together, where momentum is mass times velocity, so it's going to be m1 v1 initial, m2 v2 initial, m1 plus m2 v final. Is that okay, Jeff?
Yeah.
What are we trying to find? Folks, what are we trying to find? V final. No angles. I should have really done that after this line. I should have said, hey, any angles, any north of souths, any thetas? So I think I can just divide. I think I can say V final is going to be, in fact, I think, the same equation I get the same equation as I got, back here. I guess that's the equation that describes objects running into each other, sticking together. Let's plug and chug. V final is going to be mass 1, 2,000. V1, 15. Plus mass 2, 1,000. Velocity 2, 6 or negative 6?
6.
Which one? How do you know?
Same direction.
Same direction, okay. And I'm glad someone said negative 6. The problem is, first of all, this is going to get tougher, but already it's really, really easy with the vectors, Miller, to make a mistake, right? Over, can I add mass 1 and mass 2 in my head? 2,000 plus 1,000 is 3,000 without losing you guys? Okay. How fast will the wreckage move off together? Bracket 2,000 times 15 plus 1 plus 1,000 times 6. Probably could have done this in my head now that I think about it. 12? Okay. Now, then what? Well, then both drivers would hit their brakes, and now there's other forces. Remember, the law of conservation of energy, I said, is for an isolated system. You have no outside forces or anything like that. Did it work okay, kiddo? Darian? Yeah? Think so? Because when I see this, usually this doesn't mean it worked okay. Usually this, Darian, means you okay, fine. Turn the page. Oh, a little thought experiment. 2 eggs are dropped. Oh, turn the page. 2 eggs are dropped from the same height. Let's call it H. One hits the floor and breaks, obviously. The second one falls into a pail of water and survives. What's the main reason, in terms of physics principles, that the second egg survives? Anybody know why? The time is bigger. How would I try and explain this? You know what? I might say something like this. They both have the same mass. What can you tell me dropped? What else is the same? Okay. If they go through the same height, what can you tell me about V final for both of them if I compare them? Well, if impulse is mv final minus mv initial. And if they both have the same mass, and they both have the same initial velocity, and they both have the same final velocity, what else do they have the same? Same change in momentum. You okay with that, Jeff? But what was another way to write change in momentum? Force time. Okay. So where it says discuss your answer, I'm going to go like this. Draw a line down the middle. Change in momentum equals... By the way, what direction would the change in momentum be? Up or down on impact? Think about it. It's got to be up because the ground, first of all, has to bring the egg to a stop. Or when you, better yet, when you bounce a ball, the change in momentum is totally up. The ground brings the ball to a stop and then applies another up. Okay. What was your argument, Trev? Which one has a bigger time? So I'm going to say this. Big delta T, small force, small delta T, big force. Is that okay, using big letters and small letters to represent big and small? That's why an egg will drop. Hey, that's part of the idea behind seatbelts and crumple zones. Again, if we can just lengthen the time of collision just slightly, makes a huge difference. Makes a huge difference in survivability. Turn the page. If we look at a graph of force versus time for the egg hitting the floor, it would look as follows. What's on the y-axis? What's on the x-axis? Where does impulse appear? In here, where does impulse appear on this graph? Well, I've told you there's two possible ways. One way, don't write this down, maybe impulse is the slope. Slope is what over what? Rise over run. Maybe impulse is force divided by time, or newtons divided by seconds. Is impulse force divided by time? Is impulse newtons divided by seconds? Please, someone say no. What else could we look under graphs? Not just slopes. What else did I say? Oh, maybe it's the area. Now, if it was the area, that would be force times time, or newtons times second. Ah, that's impulse. You want to know the change in momentum? What's another word for change in momentum, Carl? It's this area right here. So here's the question. Now that I've done that little rant, which of the following graphs, A, B, or C, would best represent the force time graph for the egg hitting the water? Then it says the egg on floor graph is shown as a dashed line for comparison purposes. Actually, that vanished somewhere around 2007. I've never been able to get it back. I think I told you these were originally typed in Word 95 for Mac. So this document file is about 19 years old and it's slowly becoming decrepit. So I've lost the dotted line, but I think we can still reason our way there. What did we say? Both of these eggs are going to experience the same impulse, which means both of these eggs better have the same what on this graph? Same height? Same width? Same what? You guys are looking lethargic right now. I'm getting no energy from you. In fact, I'm getting energy pulled. I got Kylie back there, kind of. I got Darian here. I don't know where his eyes are. You with me? You back? I got Anthony just being Anthony. What did we say just now on the previous, right here? Where did we say impulse appears? On a force versus time graph, it's the area. So if the second egg has the same impulse, the second egg must have the same area. So you ready? I notice, Anthony, this width. Trevor, what did you say about the egg that survived and the time of impact? Bigger, smaller, or the same?
Bigger.
So I'm looking, you know what? That can't be right. It's not wide enough along the base. Is that okay? Then what I want to do is I want to imagine which of the remaining two actually have enough area underneath them to hold this puppy. And the way I would do it, since I have no numbers, I would probably in my mind just kind of cut each of these in half and then take this triangle and flip it like that, and this triangle and flip it a little better than that, Mr. Dueck. Kind of like that. I think I'm leaning towards this one because I think in my mind when I rearrange this, I get much closer to that area. I don't think it can be this one. Because I've lost the dotted line and the numbers, I can't give you a better, and I haven't retyped it. But I like the thought experiment, Carl. The idea is, you know what? Well, in any collision, what's your final momentum always in any car crash? Zero. We're stuck with that. What's your initial momentum? Almost certainly freeway speed, or highway speed, or city speed. But we're kind of stuck with that, whatever the speed limit is. So if we can't change the impulse, how can we lower the force that the driver endures? Increase the time of impact. How? Crumple zones and seatbelts. Most modern seatbelts are designed so that you jerk forward a little bit before it brings you to a stop. That little jerk forward, again, Jeff, we don't have to do much. Even if you triple the time from 1 millisecond to 3 milliseconds, which is not much of a delay, you've 1/3 the force that the driver is going to experience. That's a huge difference. It says explain your answer. We just did. What's your homework? Number 1. Number 2. Number 3. I like number 3. I like number 3. I like number 3. Good chance you'll see something like it in the future. Picking my words carefully. 4 is good. 5 is good. 6 is good. So far I've assigned everything. Yeah, I know. 7 is a nice review of work and energy. I'm going to skip 8. I know I've assigned it in the past, and I think I can never get the answer that's there, but I also seem to recall maybe fixing the answer, but I can't quite remember, so I'm going to nuke it. Although it's kind of cool, just, when you're bouncing something, that's a collision, and it's a nice change in direction. You have to let maybe down be negative and up be positive, but I'm going to nuke number 8. "12 is good.